तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we will have yet another session on the HBT. We have had 3 sessions focusing mainly on the gallium arsenide based heterojunction bipolar transistors. The reason for switching over to this gallium arsenide based HBT is to reduce the base width, still accommodate high doping in the base region. This is possible because in the emitter region you can reduce the doping when the band gap is large without hurting the emitter efficiency. You can still have very high emitter efficiency. We also saw how the surface effects control the performance of this device. We saw that it is important to passivate the surface of gallium arsenide if you want to get reasonable beta, reasonable performance. Otherwise, entire performance will be masked by the surface recombination effects. In fact, the first result that was done by Bell Labs, New Jersey was disastrous in the beginning, because they expected beta of about 2000, they got a beta of about 30. The whole reason was the surface effect. So, once they passivated the surface, they found that the beta goes up by a factor of 60 right up to 1800. Okay. But there were problems with stability, and that was sorted out over the several years by switching over from sodium sulphide passivation to ammonium sulphide with a coating of PECVD nitride or polyamide. So, things like that have been going on over the past decade now. So, I brought in that scenario almost up to date with gallium arsenide based HBT. Now, the other types of HBTs are gallium indium arsenic phosphide, that is a quaternary on a ternary gallium indium arsenide on a binary compound. Now, here all these are lattice matched, that is gallium indium arsenide matches with gallium indium phosphide. You add a little bit of phosphorus to that, okay, the band gap goes closer to indium phosphide. In fact, I just wanted to put that diagram. See, for example, you have, I just am drawing the diagram, indium arsenide, gallium arsenide. Okay. I am not putting the axis, etc. In the axis you have got the band gap, in the here you have got these lattice constants. So, indium arsenide. Somewhere here you have got gallium indium arsenide, where one of them is 0.47, the other one is 0.53. Now, you add, and here you have got indium phosphide. So, the band gap of that is higher than the gallium indium arsenide, and gallium indium arsenide band gap is lower than that of gallium arsenide. Now, to this ternary compound you add phosphorus. Okay. You can call, instead of gallium X indium X, etc., you can add phosphorus and arsenic Y. Okay. You can call it as like this, gallium X indium 1 minus X, arsenic Y, phosphorus 1 minus Y. We are matching all those things. So, if I add phosphorus to that, you move along in this vertical line, keeping the same lattice constant X, you move up. So, this will be actually somewhere here gallium, indium, arsenic, phosphide. Why I do this diagram is, you know that it is lattice match with gallium indium arsenide and indium phosphide. Okay? Because after all, adding phosphorus does not change the lattice constant with respect to that, because it is the same phosphorus atom which gives the lattice. Okay. Now, why should you go for this? This type of structure has benefit. One is gallium indium arsenide, as you know, has much better mobility than gallium arsenide, okay? Because indium arsenide has got higher mobility. When you mix with gallium, gallium indium arsenide has got better mobility, but in between indium arsenide and gallium arsenide. The band gap also is different from that, lower than that of gallium arsenide. Okay. Now, but you get fairly decent band gap there, but main reason is it gives better mobility. So, on the top of that, of course, you put this material which has got a wider band gap region. Now, here the advantage of gallium indium arsenide over gallium arsenide is not merely higher mobility, it has got also lower surface state densities. That is what has been seen. Gallium indium arsenide is easier to passivate compared to gallium arsenide. So, this is one of the key reasons why people are trying to look into that. And of course, added attraction is for those who are working on indium phosphide substrates, that is the material. That is of course on a lighter sense. Now, there is another HBT. So, I am not going into details of that, it is only the change in the material, but performance wise it will give slightly better performance compared to gallium arsenide. It has the disadvantage of lower band gap, of course, you pay for that in terms of lower band gap and associated effect on the breakdown voltage, etc. Now, you can have double heterojunction. In fact, when starting with the gallium arsenide HBT, I pointed out that the structure, let me just put it on the board here, okay, the structure aluminum gallium arsenide, that is N. In fact, lightly doped. Then P type gallium arsenide. This is the base, this is the emitter, this is the base, and the collector. In a heterojunction transistor, we have one heterojunction. Double heterojunction would be, you have this also, L gas. Okay. On that, you can have this may be N minus, and then you have got N plus layer. N plus layer can be gallium arsenide, but main thing is this junction and this junction both are heterojunction. What is the merit of this? The merit of that is whatever you gain here, you gain here also. When the transistor is in the active region, not a big role for this, because this layer will be depleted. But if the transistor goes into saturation, as in switching circuits, if you are not using ECL, okay, then in a TTL and structures like that, the transistor goes into saturation. Collector base junction gets forward biased. Okay. If the collector base junction is forward biased, what happens? You have the carrier concentration like that, stored charge there, this is the N. And of course, here you have got hole injection. Since this is wide band gap material, the hole injection into this region we saw it is negligibly small, Ni squared by doping. Okay, Ni squared is very small. So, the carrier concentration here is very low. So, that is why you get the higher beta. Emitter efficiency is very high in spite of lower doping. Here also it is lower doping, but you got wider band gap. So, if it is forward biased, okay, saturation, device in saturation region. If this were the same gallium arsenide, you would have got the whole concentration reached like this. Of course, I just draw a small region there to signify the transition region. Okay. You would have got high concentration hole injection like that if it is a narrower band gap material. If it is wide band gap material, what happens here? Same thing. Hole injection from the NP region to the N region when it is getting forward bias is very, very small, because the boundary value here is Pn0, P in the N region, Pn0 is related to Ni square. So, Ni square is small because it is wide band gap material. So, you will have very small injection there. So, that is what we mean by saying that the transistor will go to saturation, still you will not have the stored charge effect. Double heterojunction for switching transistors, this will be ideal. You do not have to use lifetime control techniques, etc. All that you have to worry will be the charge in that region. No charge here, short charge here, no short charge here, because it is wide bandgap material. Short charge here can be minimized by shrinking the base width. So, you are in business for high speed circuits. So, that is one of the merits of double heterojunction transistors. Okay. So, that is why I just thought I will point out this to you, because this is something which people have been exploring, but if you are working on the emitter coupled logic circuit, you do not have to worry about that, because there is no forward bias on the collector base junction, there is no saturation, it is only active. So, this is just still you can make use of that for without using ECL, you can use for high speed devices. Okay. So, you can see that bipolar is a potential candidate for high speed devices, HBT. The other one which is now has gained popularity over the past decade is the silicon germanium HBT. What is the merit of silicon germanium? Okay. Here what you do, the merit is apparently or evidently you have got silicon germanium in the base, silicon in the emitter, because germanium band gap is 0.7, silicon band gap is 1.1. Silicon germanium will be somewhere in between, depending upon how much germanium is there. So, you have a narrower band gap material and a wide band gap material. If you can grow one over the other one, still get a defect free layer, then you can make heterojunctions with silicon. So, this is where the joy of the silicon technology person is, because silicon technology is so much advanced today. If you can bring in HBT in that, then nothing like that. So, people have been working on that. They came up with the silicon germanium transistor. Compatibility with silicon technology. I can have silicon germanium transistor HBT and I can have CMOS of silicon. I can have BiCMOS, bipolar and CMOS combination, which will give real high speed. In fact, IBM has been working on it, it has been successfully, it has succeeded in doing this combination of silicon germanium transistors and CMOS, BiCMOS. Let us go through that and see why and how this gives better performance or comparable to that of compound semiconductors like gallium arsenide based devices. That is the structure. Silicon emitter, silicon germanium p type, silicon n minus, silicon n plus. You will be wondering, you are putting a lower band gap material, but that is the whole key thing here. Let us go through this quickly and see what benefits you get, other benefits. Band gap of silicon germanium, that is this base, depends upon X, that is the mole fraction of germanium. X equal to 0 is silicon, X equal to 1 is germanium. Now, the lattice constant of germanium is different from that of silicon. Germanium would match with gallium arsenide, 5.63 angstroms lattice constant. Silicon is lower than that, 5.43 or so. You may say it is just 4%, but 4% is quite large when you grow one layer over the other, because there will be at least for each 25 atoms there will be one mismatch will be there when you grow one over the other. So, if you have to grow a layer over that, how do you do that? This diagram, that this is a very popular diagram, silicon germanium people always will flash this. What you have on the y axis is the critical thickness of germanium on silicon or silicon germanium on silicon substrate. What is the maximum? See, I have discussed this earlier when I talked of strain layers. You can grow a lattice match layer, epitaxial layer on a substrate up to certain thickness. Then if you recall, I am not flashing the diagram again, but if you recall, if the lattice is wider, the top layer, it gets compressed like that and elongated that way, so that there is no defect, there is no misfit, no dislocation. You get single crystal, but a strained layer. That is better than a defectful layer. So, now if you keep on growing, the stress keeps on building up. At a particular point, the bonds will break and you get defect. This all we have discussed earlier, just recall that. So, there is a maximum thickness layer that you can tolerate which does not have defect, but it is strained. So, the strained layer maximum thickness you can see here. This curve shows you one of the theoretical calculations which has been made, strain equilibrium. Just when the strain is in equilibrium, the maximum layer. For example, I can grow germanium on silicon, but thickness of layer that you can grow is about 10 angstroms, just maybe 2 atomic layers. Okay? But you keep on reducing x, go towards silicon, you can see I can grow even 1000 angstroms. 0.2, x is 0.2, 20% germanium, I can have grow a layer which is defect free about 100 angstroms. This was initial theoretical value. But if you do this growth by ultra high vacuum technique like MBE etc., you can get thicker layers which are defect free. In the sense, as you grow, you do not provide that high temperature required for them to break up the bond. So, it grows without breaking the bond for thicker layers. That is what is shown here, dotted line. Dotted line is actually the one which is called as metastable, in the sense you grow it at lower temperature, though at this point it has a tendency to create defective layers. If you grow at lower temperatures, you can get thicker layers, not too much thick. You are not pitching upon very thick layers. Base width you are talking about 0.1 microns. So, you are happy with that. If you are able to get 1000 angstroms, that is quite sufficient. See, there are, I do not know whether you are able to see, there are 1, 2, 3, 4, 5. Those are the experimental points. People have grown silicon germanium by MBE and found that strained layers which are defect free can be grown with that thickness. That matches with this curve, dotted line. So, what we are telling is I can have 0.2 x, still get unstrained, still get strained defect free layer which is about 2000 angstroms. Okay. Now, that gives us confidence in this technology and people have gone ahead with making these devices. Let us take a look at the band gap. There are a number of curves here put. All that you have to understand is, if you just have a silicon germanium alloy, you will get a band gap, some particular band, no strain. Just make an alloy of silicon germanium, single crystal, grow a thick layer, the intermediate layer will be defective, but top layer will be silicon germanium which has no defect, thick layer. That is not suitable for the making HBT, but if you do that, that will be the band gap, the top curve. Germanium 0.72, silicon slightly more than 1 point, in fact people talk of 1.11, 1.15, that range people talk of. So, this curve shows it varying from about 1.15 to, it all depends also on what temperature you are measuring that, 2.72. But what we are talking of is now silicon germanium which is strained. The top layer is unstrained silicon germanium. So, strained layer, when the layer is strained, the lattice is under stress and the energy band diagrams also undergo changes, and because of that you get different band gap. In fact, you get lower band gap. So, you can see here, in fact that suits you. You can mix very small quantities of germanium and still get a band gap which is lower than that of silicon. See, the top curve here is unstrained silicon germanium. This curve, this particular curve is actually the one strained silicon germanium on unstrained silicon. You take silicon substrate N type, grow silicon germanium, that is a strained layer, then this is the band gap that they have estimated. Okay. So, you get a band gap which follows this rule, which is much smaller than that of silicon germanium unstrained. Okay. So, you can see for about 0.2 you will have about 1 electron volt. Instead of 1.15 here you have got 1 electron volt. So, you have got about 0.15. If you use about 0.2 in that ball point, you got a band gap, a material which is strained, but which has a band gap definitely smaller than that of silicon by about 0.1 at least, 0.1 electron volts. That is good enough to get that e to the power delta Eg by kT, e to the power of 4, 50 times more. Okay. What is the benefit of using that? Now, let me go back to this diagram. So, you can put a layer of 1000 angstroms very comfortably with the base width 1000 to 2000 angstroms, layer width, base width, which is band gap which is smaller than that of emitter. Now, compared to the silicon NPN transistor, silicon germanium base, if you change over, what benefit you get? We have seen already what benefit you get, you can dope that region heavily. Apart from that, even in gallium arsenide based devices, that holds good. Collector current IC is larger for a given VB. How do you say so? The collector current, we have been writing this expression on and off, okay, that depends upon QDNB Ni squared by total integrated doping, V to power VB by VT. It is a very familiar formula for you. So, you know that you can increase the doping for a given current, okay, or you can actually, when you reduce this band gap, Ni squared goes up. If Ni squared goes up, for everything same, the IC goes up exponentially. Ni squared is proportional to e to the power minus CGB by KT. So, the collector current is larger for the same VB. What I am comparing is a silicon bipolar junction transistor and silicon germanium base HBT. Silicon germanium base HBT will give higher collector current, okay, for a same VB. In other words, you can go to lower VB to get the same current. Okay. You can go to the active region, okay, go to the active region. How is that? That is the way the carrier concentration is. Now, if the band gap is smaller, you get a larger current. Okay. How do you do that in this diagram? This is fixed, that goes up, and it is like that for the same voltage, because after all NP0, okay, NP0 is equal to NP0 e to the power of Pb by Vt, and NP0 is actually minority carrier concentration, thermal equilibrium. Okay. For a given doping, when Ni squared is larger, this will be larger, that is why that is larger. NP0 minority carrier concentration larger if the band gap is here. Ni square divided by Pp0, which is Ni square divided by doping. That increases, and that increases, NP0 increases, current increases. This is a simple way of understanding from the formula we have put it in that slide there. Okay. So, for a given voltage, the current is more. This current does not change. What is injected to the emitter? Total current increases. So, what is the impact of that? The impact of that is beta improves. Collector current increases means beta improves. Okay. Base current does not change much, because the base width we are talking of is very small. Volume recombination you saw, it is negligible in a HBT. Okay. It all depends upon the emitter efficiency. Then IC increase decreases the emitter charging time or any charging time for a given VB. Okay. For a given change in collector current, the collector current change is more for a given change in VB in this case compared to HBT, BJT. So, all the charging times are smaller, particularly the emitter charging time is smaller. This improves the switching speed. Okay. This is a well known fact that if the currents are larger for a given change in voltage, the switching speeds are large, even in integrated circuits as a device as it is, because after all the cutoff frequency will be dependent upon the transit time in the base and the charging time in the emitter base capacitor charging time. The emitter base charging time depends upon how much the current is, that is larger here for a VB. You have to charge a smaller voltage to get a particular current, okay, or for reaching a particular voltage you have a larger current available, so it charges faster. That is why the charging time of the emitter base capacitor is smaller, so speed is higher. Another very important advantage which is there for all the HBTs okay, but mainly exploited in the case of HBT silicon germanium transistors is this factor. Germanium content X in silicon germanium can be controllably graded across the base. I do not know whether it rings the bell. As I move from here to here, I can vary that germanium content. I can make the germanium content more here, I can keep on changing that. That means I can vary the band gap across the base, narrower band gap, wider band gap here. Okay? You can do that by just varying, while growing, vary the mole fraction of germanium by adjusting the flow rates or by adjusting the germanium content in the MBE. So, you can vary the band gap. What do you get out of that? You get, of course, the band gap change. What you get is, if you change the band gap, that introduces an electric field. You remember, when I draw a diagram like this, the carrier concentration is linear, varying injected carrier concentration. What we are assuming is the carrier transport is through diffusion. There is no electric field here, and the transit time is W squared by 2dn. You can increase the speed or reduce the transit time by, not only by reducing W, if I can bring in electric field, the transport will be faster. The velocity by diffusion is smaller compared to velocity by drift. So, if I introduce drift by some means, I am in business. I can increase the speed, transit time can reduce by a factor of 5, 10. So, from 10 gigahertz you may go to 100 gigahertz. People go that. 100 gigahertz is not a joke, it is a reality. It is not a myth. People have reported 100 gigahertz silicon germanium transistors, HBT. One of the reasons is this. You can introduce that. I will just quickly go through the analysis of this. Okay. Now, this is as a statement I put here. You have electric field which aids the electron transport across the base, thereby decreasing the base transit time. When I say an electric field is present in this here, which aids the transport of electrons, the field direction is plus here, minus there. Electrons are moving in that direction. It attracts towards the positive terminal. So, there is a field in this direction. A built-in field comes in. You can see the next diagram, you will see it clearly. So, when tau Tb is of course reduced, Ft is better due to smaller transit time. That diagram tells the whole story of grading the band gap across the base. I just put of course both conduction band and valence band. It could be that valence band is not changing, only the conduction band also, but I have shown both. Now, what we are interested in is seeing the impact of this change in this conduction band and valence band. That is, you can see smaller band gap Eg at Wb, larger band gap Eg at 0. I hope you would understand that the x that I am using here is for the distance. I tried to change it, but I was stuck with the thing, so I am just keeping that. This is the x is the distance. It is not the mole fraction that we are talking of here now, when you write the equations. Okay. X, only when you have silicon germanium, there we can put x is the mole fraction, but this is actually the distance. So, you can see if I have an energy band diagram like this, conduction band like this, what does it mean? Okay, whenever there is a tilt in the band gap, there is an electric field. A tilt in the band gap like this would mean that this is positive here, minus here. Okay. So, the electrons which are injected here find themselves in an electric field which push them in that direction towards the collector, drift velocity. You do not worry about this, what is happening to the hole here, because you do not care about the holes now. In fact, in this type of thing, the electric field, the nice thing about this added thing is, if you have a band gap like this, the electron field for electrons will be in this direction, the field for holes will be in the other direction. So, you have the holes are being prevented from moving into the emitter further, emitter efficiency further improves. This is a classic thing of nice thing about this type of structure, band gap varying continuously across the base region. Okay. So, E g is a function of x now. In fact, what you can understand also is, we will come back to this if you have time to see the physical meaning of this, but right now from the diagram itself you can see there is electric field like this. Whenever there is a band gap changing like that, field is plus on the lower energy side and minus on that side. Okay. Now, let us go back and see what is the magnitude of this field. Very quickly we will rush through that. Very simple equation. Instead of writing the current as due to diffusion alone, since you know that if there is electric field, you have to write diffusion current and drift current, Qdn dn by d of x. I am writing this equation at thermal equilibrium, no bias, you are not applying any bias, Qdn dn by d of x. And so, when I am putting it NP0 thermal equilibrium, and it is a function of x. Okay. And Qnp0, Qn mu n T E is electric field, that should be equal to 0, no electron current transport condition under thermal equilibrium conditions. Okay. Np0 is actually the thermal equilibrium value of Np, electron concentration in the p region. If I remove the 0, it will be actually injected carrier concentration, and is a function of distance x from the emitter to the base, from the emitter base junction. Why? Because Np0 is Ni squared by Pp, and Pp is the doping. Okay. Doping may also be function of x. Even if it is constant, you will have the Np varying. Even if it is constant, if the band gap is varied, Ni is varying, Ni is actually increasing as you move from the emitter to the other end. So, Np actually increases, thermal equilibrium constant value is more in that region as x goes on. Okay. Now, what you have to do is to find out the field, you have to equate this current to 0 because it is thermal equilibrium. There will be concentration gradient existing, but if the current flow has to be 0 when the concentration gradient is present, the only way possible is presence of electric field, that comes in because of this charge redistribution. So, that electric field is the one that we are going to find out. Equate this diffusion current to drift current and plug in this Np0 equal to Ni squared by Nax. So, I have rewritten that equation, that is instead of Np0, now I am putting this Ni squared by Na. So, Qdn d by d of x Np0, which is Ni squared by Na, Qnp is Ni squared by Na mu n T, that is 0 in thermal equilibrium condition. That is what we mean by that equation 1 and 2. Okay. Now, all that you do is differentiate this. So, when I differentiate that, first term, second term I am retaining as it is here, Q Ni squared by Na mu n T is retained as it is. Remember, Na may be a function of x. So, we will take that also into account, and E is a function of x. And the first term, if I take Na also is a function of doping, then I get Qdn 1 over Na pull out UDP formula, first function to differential of second function, that is 1 over Na, differential of second function is d by dx of Ni squared. I am not differentiating right now, keeping it like that, minus plus second function, that is Ni squared into differential of 1 by Na, that is minus 1 by Na squared into dNa by d of x, because Na is function of x. If Na is independent of x, that term goes off. Okay. So, this term is written here. Now, E is given by equating to 0. So, what I do is I find E equal to, I take all these things to the other side, divide by Q Ni squared by Na. Let us take this term for example. Okay. Let us take this term, divide by Q Ni squared by Na, Ni squared by Na, that when you do, you get that. Just rearranging the things, what you get is actually electric field is equal to dN by mu n. You just see it here. you get dn by mu n. When you divide the whole thing, dn by mu n is there for both the terms, and in this term Na square cancels and you get 1 by Na, and this, since it goes to other side plus, so you get dn by mu n 1 by Na dn by dx. Similarly, the second term becomes dn by mu n 1 by Na square d by dx. You can just see it for yourself by just rearranging those. Okay, this is what you get. Now, so electric field dn by mu n is actually equal to Vt, Kt by Q. So, Vt by Na dna by dfx. In fact, this is a very familiar formula for some of you who have taken more courses. If there is a doping gradation, there is an electric field due to built-in field due to that. Wherever the doping gradation is there, that is the first term. You get now additional term due to the band gap variation, that is Vt by Na square d by dx Na square. Now, let us take a look at that. Now, this Na square is actually proportional to e to the power minus Eg by Kt. So, I differentiate this and divide by Na squared. So, d by dx Na squared is actually, when I differentiate that, you get minus 1 by Kt Na squared, because the exponential term. When you differentiate this with respect to x, you get Na squared itself, because it is exponential e to the power minus k, okay, minus Eg by x by Kt. But 1 by Kt into differential of the d by dx, df by dx, okay, a function, it is a function we are differentiating once and that, simple differential equations, differential formula. So, that you get, because when you differentiate you get whole term on the numerator by Kt, differential of this, minus is there because of that. So, I plug in this quantity into the previous equation, which actually has Vt by Na squared, Vt by Na squared into dEg by, just go back to that. See here, first term is Vt by Na dna by dfx, that I am retaining as it is. Second term, I am substituting for d by dx Na squared, which is nothing but minus 1 by Kt into dEg by dx into Na squared. Na squared cancels, so I get that. Okay. So, what you get now is Vt by Na dn by dfx plus Vt by Kt dEg by dfx. It tells you totally now that the electric field is decided by doping gradation plus gradation in the mole fraction, that is gradation in the band gap. Okay. Now, let us take a look at that. Okay, that was missing there. So, this is the formula that we have got now, which tells us what is the electric field, thermal equilibrium. Now, when you forward bias emitter based junction and inject carry electrons, that electron experiences this built-in field. Okay. And what is the direction of this field? dn by d of x. If the doping is changing from here to here, more doping and less doping there. If there is doping, actually if you do a diffusion, it will be higher doping here and not e to the power minus x by L, something like that. Exponentially it is falling. Then the field actually will be dn by dx is negative, it will be in that direction. Okay. What about the second term? dEg by d of x plus dEg by d of x. Band gap, if it is going on falling here, Eg is going on falling, that also in the direction. Both are in this direction. Both the electric fields actually support the faster movement of electrons from emitter to the collector. So, this is the added benefit that you get for silicon germanium Hvt compared to BJT of with silicon alone. Okay. You can also put this term particularly as Vt is, sometimes you will see this put as Vt is Kt by Q. So, that becomes 1 by Q. So, 1 by Q dEg by d of x. Okay. The first term is due to doping gradation and gives electric field component aiding the electron flow, provided doping gradation is in that direction from the emitter to the base collector. which is usually the case when you do diffusion. Take a substrate, diffuse from top, doping is higher on the top. So, as you move down towards the collector, doping is reduced. Okay. So, that is aiding the electron flow. What about second term? Second term is due to the band gap gradation and aids electron flow if dEg by dx is negative, which means actually the band gap at the collector edge must be at Wb should be less than the band gap at the emitter base junction edge. Okay. Right. Now, get an idea of what sort of fields are there in the transistor. If you see here, this is 1 by q dEg by d of x. That is the second term. We are seeing what is the magnitude of this field due to the band gap narrowing, band gap gradation. That is that. Okay. For a linear gradation, in the sense you have got that linearly varying the band gap, delta Eg varies as a function of x linearly, then you got delta Eg by d of x. The negative sign is there. Okay. That minus that by Wb. Okay. Your dEg by d of x is negative, that is why it is put there. Magnitude is that quantity, is delta Eg by Wb. Now, delta Eg, if it is 0.15 electron volts, if you vary the band gap from the collector to the emitter by 0.15, then for a 0.1 micron base width, see you can get still a strained layer which has band gap which has no defects. Electric field is from 0.15 by 10 to the power minus 5, 15 kV per centimeter. So, this is the benefit that you get, current flow by drift and diffusion. Now, couple of things I want to point out here. If you take the electric field in the case of doping gradation, what sort of electric field that you get? Okay. Just let me put that. If I take the Na x equal to Na 0 e to the power minus x by L. Okay. What is electric field? No band gap gradation. This you get all the time in the case of BJT. All the modern BJTs have an electric field built in the base because of this gradation which you saw just now. That is actually what? Vt by n of x. Okay. Na by x, dNa by x, d of x. We just now saw. Go back and see that term, that is due to doping gradation. In fact, you can derive that equation right from the fundamentals when Ni is constant. You will get that only one term. Okay. With the way we started, we have taken Ni also varying, Na also is varying. If you take Ni constant, you will get second term dropped out, because delta Eg by d of x 0. So, here if that is the thing, what is the electric field? Where L is a constant, the decay constant for the doping. What is the electric field? Vt by L. dNa by d of x is this into divided by L, okay, and that is the quantity. Okay, you will get that electric field minus, that is minus. From here the minus sign comes, and this tells you that electric field is in that direction. So, minus sign is right, it must be there, otherwise whatever we have been telling is not correct. Minus sign comes from there. In fact, that tells dN by dx is negative. Okay. So, it is a constant electric field. What will be magnitude of this? Okay. What will be the magnitude of this quantity Vt by L? Some idea we must have. That depends upon L. How much will be L? Let me just go back down here. See, Na naught is Na0. Na at Wb is Na0 into e to the power of minus Wb by L. What I am getting at is that field depends upon base width and L. So, therefore, Na naught doping at the emitter base junction edge divided by Na at Wb is actually equal to e to the power of Wb by L. Okay. So, this Wb by L therefore depends upon logarithm of that. Supposing Wb, see, you will get the benefit of this only if doping here is smaller compared to doping there, gradation. Okay. When you have doping concentration like this, 0 and x, some variation like that, Na0 and that is NaWb. That is what you are talking of. Exponential doping concentration gradation, doping variation, you will get it like this. Now, Wb, supposing this ratio is 100 or let us say this ratio is 54, doping at the emitter and doping at the collector edge, that ratio is 54, which is reasonable to assume. What will be the factor? 4. E to the power 4 is 54. Okay. So, if this ratio is 54, you get this as e to the power of 4. So, W by L is equal to 4. Okay. If W by L is 4, if Wb is let us say 0.4 micron, I am just giving some example. If Wb is 0.4 micron, L will be equal to 0.1 micron. I am just computing some number, saying what is the order of this field here. This is 54 ratio, this is e to the power of 4, that means W by L is 4, Wb field is 0.4, L is 0.1. So, if L is equal to 0.1, I am just computing the magnitude, what is the order of this L? It may be 0.1, 0.2, whatever. So, if it is 0.1, what is the Bt by L field now? 25 millivolts divided by 0.1. So, for this case, this is actually minus, let me just put it up here little bit, minus Vt by L, which is actually equal to 25 millivolts minus 3 divided by 10 to the power minus 5. How much is that? This is 2.5 kV. I just took this example to illustrate that you will have in the conventional transistor itself a built-in field of this order. In fact, the factor W by L is called the field factor which actually decides what is the potential change there due to that electric field. Okay. So, you have this much field, and you saw also in this case I have taken an example where the base width is 0.4. If I take the same example, the base width is 0.1, 1/4 of that will be 4 times that, 10 kV per centimeter. Okay. I took a wrong example there, L equal to 0.1, taking Wb as 0.4, but if you have to compare with that, Wb equal to 0.1 micron, and if this is 4, L will be 0.1 by 4, this will be 10 kV per centimeter. Okay. So, just depends upon the base width and the doping gradation there. In other words, it depends upon W by L ratio, okay, and that L depends upon W L depends upon doping concentrations. Okay. Now, let us go further down into that. This is a structure that now we can run through the people results that they have been reported. They have made devices which can go right up to 100 gigahertz. You go to website and say, see silicon germanium HBT, you will see IBM results put across. They have made BiCMOS, they have made ECL, all sorts of things with the silicon germanium technology. So, it is a big contender for gallium arsenide technology, silicon germanium. This is the answer challenge thrown by silicon technologies towards gallium arsenide based HBT. But still your high electron mobility transistor stays there, there is no contender here. Okay. That is one thing that you have to remember. But there are other issues which when you want to go to harsh environments like higher temperatures, you can't use base materials which have smaller band gap. Silicon germanium has a smaller band gap compared to gallium arsenide, etc. So, those harsh environments still you have to take a look at the gallium arsenide based devices. So, this is the type of structure that you see. See, in bipolar technology, you have got in the integrated circuit, you have the P minus layer substrate and N plus collector, contact section from the top, then N type layer collector. You can see the narrow P plus epitaxial base, which is of silicon germanium, and contact is taken laterally there. This, of course, I am not going through technology of this. This is a self-aligned technology where you can grow layer by layer without too much difficulty in aligning with single alignment marks defined already. You can realize this. So, this is that, and this is the emitter base collector. Emitter is polysilicon, N plus polysilicon. Okay. This is another thing which actually is very attractive for self-aligned techniques, and also you put N plus contact, it is slightly diffuse into that region, into this region, and make a single crystal very shallow N plus junction or N type junction, and then a contact taken onto this N plus layer. Okay. So, this is the structure here, and of course, you have got these techniques people use for this silicon technology for trench isolation, etc., where you put a trench, oxidize it, put polysilicon. Okay. All those techniques are there for isolating devices and integrated circuits. This is the approach that IBM has been using, and the layers, the device structures are micron. Doping profile, I will just quickly run through this because there is no more explanation needed. Here they did not, this particular structure that is used here does not show doping concentration changes. Arsenic emitter doping, base doping gradation, and germanium, they have not shown that gradation that much in this case, but you can see from here to here the gradation is there. Germanium gradation is there, that is band gap is varying from larger to smaller value as other way. There is a built-in field coming up. Okay. And percentage of germanium right up to about 10%, 0.1. So, band gap is narrower compared to that. As I said right at the beginning, collector current is larger in the case of silicon germanium BJT compared to there are two curves, collector current in the silicon germanium HBT, collector current in the case of silicon BJT. So, that is about a factor of 4.5 larger, due to the one is the field, other one is heterojunction effect, both. Base current same, and device size you can see 0.5 by 2.5 micron, very small strip for the emitter. Okay. That reduces all the capacitance which are involved. Then cutoff frequencies, once you get actually larger current for a smaller voltage, the charging times are all smaller, you get much higher cutoff frequencies. For this particular device, which has been reported quite some years back, this collector, the cutoff frequency depends upon the collector current, because that gives better charging capability for the emitter base junction. So, that is why you get, as you go to higher currents, you get higher cutoff frequency. But what you have to do is compare the single crystal BJT, much higher. What is 20 or 25, you get about 50. But now this is not, this is an older result which I am putting here, but I have seen 100 gigahertz. This is all gigahertz, 50 gigahertz. A beta couple logic circuit they have made. There, BJT, if you get 30 picoseconds, the gate delay, unloaded of course, or fan out 1, fan in fan out 1, that is 30 in the case of BJT if you have minimum, here you get 20 for HBT, silicon HBT. Okay. In fact, they have gone down further below that, picosecond range gate delay, okay, much lower than that when you go to gigahertz. So, these are the merits that you get with the case of silicon germanium. In fact, I think I do not discuss more about these things. So, in summary, the silicon germanium is playing a very key role today. A lot of people are putting their effort because you can realize silicon germanium transistors, bipolar along with CMOS integrated circuits. With that note, I will close on today. We will take on circuit aspects next lecture.